Okay, so we had our step equation telling us the amount of the electric field in the z direction coming from each little arc of angular thickness delta theta. And when we solve this numerically, we just do a whole bunch of delta thetas all the way around, add them all up, and get the total z component of the electric field. Now that's not going to be quite accurate because an arc is not a point, it's an arc. But if we make the delta thetas smaller and smaller and smaller, it comes closer and closer to being accurate. If you have a really, really tiny, like a billionth of a degree, then a little arc that thickest might as well be a point. It's going to make very little difference to any answer. So we can do our usual calculus trick. We can take the limit as delta theta goes to 0. So what we know is that the total electric field z component is going to be the sum over all the angles of all the delta e's. And if we take the limit, so that's going to be approximate, so it's going to be exactly equal to the limit as delta theta tends to 0 of all the delta e's. So that means as you make the delta theta smaller and smaller, that also means you have to have more and more of them. So if delta theta was 10 degrees, there are going to be 36 of them round. If you turn it to 1 degree, there are going to be 360 around the circle. It's going to get more accurate. If you make it 1,000 times smaller, there are going to be 1,000 times more. It's going to get even more accurate. As you make them smaller and smaller, the limit goes to 0. The number of these things goes to infinity, and your answer should get to perfect accuracy. And that means you change the sum into an integral sign. That's the marvel of calculus. So it equals, let's have all the constants first, 1 over, the thing we're integrating over is theta. We're going around the circle adding up all the bits. So that's what I'm integrating, that's why it's got a delta theta over here. So everything that doesn't involve a theta is a constant for this purposes. So we've got 1 over 4 pi epsilon naught q over 2 pi z naught over r plus z naught squared to the 3/2. And now we're going to do the integral from 0 to 2 pi, all the way around a circle, of d theta. Now that's a pretty easy integral. I hope you can all do that one. It's just going to be theta. So that goes to theta from 0 to 2 pi, which of course comes out as 2 pi. So what we find is that the z component of the electric field is just 1 over 4 pi epsilon naught q. The 2 pi from here cancels out with the 2 pi from there. Z naught all over r plus z naught squared. There should be a squared up there to the 3/2. And that's the equation for the electric field along the axis of a ring of charge at some distance. We can check this. First thing to do is check units. We'd expect it to have the same units as Coulomb's law, which is 1 over 4 pi epsilon naught r squared with the q on top. So the constants are all the same. The only real difference is you've got a z on the top and an r squared plus z squared to the 3/2. So r and z both have units of length, so it's basically length squared to the 3/2 gives you length cubed with the length on top, so length over length cubed gives you 1 over length squared. So units, good. Same as in Coulomb's law. As you'd expect, as we're just adding up Coulomb's law. We can also check the numerical answer by plugging numbers in, and it turns out we get exactly the same electric field as we get from Excel or Python, so that's another check. We can also check the functional form. Now when you're in the middle, remember, in the middle of our loop, there should be no z component of electric field. And indeed in the middle, z naught is going to be 0, so it will indeed go to 0. This is always going to be positive. This is positive on one side and negative on the other, so that's also good. When you're a long way out, we want it to look like Coulomb's law. So when we're a very long way out, so z naught is much bigger than r, this means this term on the bottom here, we can ignore the r squared. So Ez is going to be approximately equal to 1 over 4 pi epsilon naught q z naught all over, and Z0 is much bigger than R squared. We'll just treat that as Z0 squared to the 3/2, which comes out as 1 over 4 pi epsilon naught q over Z0 squared, which is Coulomb's law, being 1 over R squared with the right constants. So this seems to check. It behaves correctly in the limiting cases, its units are good, it gives the same answer as the numerical calculation. All looking good.